Okay, thank you everybody. So we're going to talk about a journal paper that we published like 8-9 months ago. And this is part of a work on hybrid planning or discrete continuous task planning. And I will start with the motivation to explain how it fits into the grand scheme. And then I will dive into the optimization. And for those of you who are not coming from control, I'm sorry. No. Okay. So how do I start? Okay. So we have a task. We have a drone that needs, for example, we have a drone that needs to take a package, deliver it, go back. The fuel might run out in the middle of the mission. And we have a start and final state. And we have discrete actions like fly, deliver, fuel, pick, and such. And we have continuous actions. We need to fly from a point, a continuous point, to another continuous point. And we have velocities. And of course, we also have temporal constraints. We can have fuel that can be depleted. And that's the setting of the problem. And for the sake of this talk, we assume we have a planner, a simplified model planner, that can give us a plan based on a simple model, simple dynamic model. So I will focus on the continuous part of the plan. So the continuous part is basically just a sequence of continuous variables, continuous values of variables that, for example, for the drone problem is just move from point A to point B to point C to point D. So, and we need to plan a trajectory for the system between these points. So sounds simple enough, but not. So in this work, the simple model planner that we use is Scotty activity, and it plans with a first order dynamics, which means that it's only a linear change in the position. So we have continuous, we have a constant velocity, and it can change rapidly between when we switch between the discrete actions. So obviously, this kind of trajectories and solution are very nice, very pretty, but there is one problem in them. They are not physical because a real system cannot change its velocity between one value to another instantaneously. So while these solutions are very pretty, they are not fit for the real dynamical problems. So what we want to do in this work is to take this plan, which you can get from a planner like this, and try to verify it. And if it is verified, we can do a trajectory planning and get a trajectory for this problem. So what we're going to do is basically going to go action by action and verify the plan. So we used the tools from optimal control. And the specific goal of this work is to compute a trajectory between two sets of points, between an initial state and a final state. When we do that for each action in the plan, we can first get a solution and see the trajectory. And if it fails, we know which action is the action that causes the plan to fail. So we can actually do something about it and to tell the high-level planner what to do. Okay, so a little background on control, on optimal control. So we have an optimization criterion, and it's a dynamical one. This is the optimization in general. We have a dynamical system which governs the whole process. We have an initial state, a final state. We can have constraints on the input to the system, and we also can have constraints on the state. In our case, it will be velocities. And we solve that by using Pontryagin maximum principle. So we write the Hamiltonian of the problem, and we augment it with the state constraints over here. We write the state and the co-state, it's the dual variables of the problem. We maximize it, and with that, we can hopefully get a solution. And in our problem, I will start with the model. So we used a model, a second-order nonlinear model with a quadratic drag. So the good thing about this model is that it's continuous. So we're going to get, when we need continuous in the velocity. So we're not going to get any jump in the velocity. And because we have this quadratic term, it's a little more physical than just a second-order integrator, and we can hide within this term, we can hide higher-order dynamics. We also have the input constraints, and we have velocity constraints, and we have the initial and final states, which we get as the assignment from the high-level planner, in our case, Scotty. The criteria for the system is time and energy. The one here stands for the time. When you integrate it, we get the time and the energy, and we can, by using an alpha term, it's a design parameter, we can, if we have the freedom to do that, we can balance between use of energy and the time of the system, the time of the trajectory. So one thing that we notice immediately that we don't see in linear models, in the linear first order model, that even in this pretty simple model, we get that the velocity is not bounded really by the constraint on the velocity, it's bounded by also the constraint on the input and the dynamic of the system. So it's not in the first order dynamic, we don't see that. So it's behavior that arises only in more complicated dynamics. Even here, we can see that. So, and the second thing, we see that the solution can have only two types of trajectories. And what I illustrate here is the trajectory of the velocity. So the velocity may get to the constraint, or it may not. So we'll only accelerate and decelerate. We also need to get a condition which tells us in which solution we are in, so we can verify if it's okay. So now we're actually diving into the optimization. We can see that only the upper constraint on the velocity is going to be active because we're not moving backwards. There's no sense in that. And the Hamiltonian is going to be constant because of the transversality condition, and the Hamiltonian is not time dependent. We're not going to too much detail in that. And this is, okay, here it's written better. This is the Hamiltonian of the problem. And the co-sets equations are these equations. As you can see, it's also differential equations, which we need to solve while we solve the problem. The control is dependent on the second co-state equation, and it's linear in that equation. And if we solve that, we have the control explicitly. And since the control is also bounded, we have this term that tells us what is the actual value of the control. So we'll start with the first case. The first case is that we're doing acceleration. We're moving in constant velocity, and then we decelerate to the final value of the position and velocity. So we see that we have that the velocity is lower than the bound, and we accelerate to it. After that, we're going to move in a constant velocity, and after that, we're going to decelerate to the final condition. So we have three segments to the solution. We'll start with the first segment because the other two are pretty obvious. So the first segment is between time 0 and time t1. T1 is the time that we switch between acceleration and constant velocity. And because the velocity there is 0, then we is constant, sorry, then we can get the equation for that, and we know what is the value of the velocity. It's the bound, and we can get the value of the second co-state from the fact that the Hamiltonian is constant, and again, we know the velocity there. We can get the value of the first co-state. In this case, because it's constant, it is the value of the co-state. And since we have these values, we can integrate backwards and find the solution. Before we do that, we need to check what is the value of the Lagrange multiplier. Okay, so the Lagrange multiplier is the one that handles the state constraint. While we're not on the constraint and it's not active, the Lagrange multiplier is 0. While if the constraint becomes active, it has to be greater than 0. So we get a condition like this. It has to be greater than 0. And because we get this condition, we can get a necessary condition which tells us if the final velocity is lower than that, well, it has to be lower than that value. If it's higher than that value, we're never going to get to the bound. So we'll never have this type of trajectory. We'll only have an acceleration-deceleration trajectory type. And we have the explicit value. And as I said, because we have the values at T1, we can integrate backwards and find the exact solution for the trajectory in that segment. These values are the same at T2, the time that we start to decelerate. We know the final condition. We can integrate forward the equations there. We can get these two segments. From the difference, we can get the middle segment, and then we have the whole solution for the trajectory. And we know the final time, and we know the control. If we cannot do that, then we know, and the condition is satisfied, we know that this solution is not feasible, and the assignment for the values are not good, and we cannot actually execute this kind of trajectory. The second case is the one that we only accelerate and decelerate. So basically, we're going to follow the same logic in the solution. So we know that when we switch the derivative of the velocity is 0, we know that we don't reach the bound on the velocity. And we can get values for the two co-states. The problem here is that because we are not reaching a specific value, we don't know the specific value of the velocity. So we denote it by Vm. And then we do the integration with Vm, and we get a parametric solution, which we can then optimize and find the exact value of Vm. And if we can do that and it's within the bounds and everything is OK, then we know that this solution is OK. If not, again, we can tell that this specific action we are checking cannot be executed. So two simulations to illustrate how an actual trajectory looks like for a second-order system with quadratic drag. So this is the case where the bound is active, so we accelerate, then the bound is active on the bound, the velocity is on the bound, and then we decelerate to the final condition. This simulation was compared with a numerical solver, Dido. Just for an anecdote, the time that it takes Dido to solve this very simple problem, it varies between 1 to 2 minutes. For us, because it's an explicit solution, we get by a few milliseconds. So we can do that very fast. The verification is very fast. This is the second case where we just reach some maximum velocity which is lower than the bound, and then decelerate. So this is how it looks like. We can see the bounds on the controller are also active in part of the trajectory. Okay. So the last thing we did in this paper is to check what happens in two cases. One, that alpha is very low, which means we really care about the time. We want to find a minimum time solution, and it looks very similar to the minimum time solution, which it's on the bound when not like this. And then when the velocity is on the bound, we can get some singular control, so it's another value. I will emphasize in this case that it looks like a bank-bank solution or bank constant bank solution. In a later paper, we actually analyzed this, and we saw that it's not like that. It approaches that, but when it's a pure minimum time, there's a singular solution, a singular control, and there it's a bank-bank, and here it's not. It's really a continuous solution in the velocity. Okay, so this is how it looks like. Again, for us, it looks like it's really a bank-bank, but actually, when we analyze it, it's not. And this is when it's a bang-bang. The previous one was a bang-zero-bang. This is a bang-bang. And the second case is when we have a fixed amount of time to execute the action. So most of the times, we're actually going to get that because the planner is going to tell us, do this action, move from point A to point B in t time. Okay, so we actually know what's tf. We don't need to calculate it. If we have the margin to play with, we can do that, but usually it's fixed. So we get a minimum energy problem, so we want to find the minimum energy trajectory. So again, we write the Hamiltonian of the problem. We follow the same logic as before. We have the co-state equations, and we have the Hamiltonian, exactly as we do before, but now because we don't know what is the velocity, and we don't have, and there's another residual, then the optimization is a little more complicated, not by much. It still works very well and very fast. And the solution looks like this. So this is a case where the minimum energy solution reaches the bound. So here we are on the bound. And this is a case when we do not reach the bound, and it just accelerates slowly and decelerates slowly to the final value. So what we did is basically we used tools from optimal control to aid the search and the task planning problem. It's good for verification of a given solution. When we get a candidate plan, we can verify it. We can verify it if it fails because of time or because of resource consumption, and we can say exactly where in the problem it fails. And after that, we can devise a solution on how to guide the planner not to fail in those points. We did some extension for that. We published it 2 weeks ago, actually. We did the structure analysis. Apparently, there's a structure analysis that is kind of special for this case. For the pure minimum time, we actually found analytical conditions that we can use in the validation stage, which I presented in PlanRob like two days ago. And for future work, we want to do that, to use what we found here to actually find a new schedule. When you get a plan from a planner and have the sequence, maybe you can find a different schedule and a different continuous variable allocation that will actually work. Okay, because in this way we can say this allocation cannot work, but we want to change the plan so we can make it work in the same sequence of actions. And we need also to put it together to make a full planning scheme that can actually plan a real plan, actually give us a real plan. So that's it. Thanks.
Other questions? None so far. I was wondering how standardized the problems are that you are tackling, whether it can, for instance, express by PDDL how far it is away and closely related, whether it's so far away that you're the first tackling these problems, or whether you could compare to other approaches.
Okay, I can compare to other approaches because there are hybrid planners out there. Okay, so they're using first order dynamics, and there are works that's trying to go further than the first order, so there is what to compare to. In PDDL, it's harder to express the dynamics, but the problems are problems that you see in PDDL also, and they're real world problems because, for example, the motivation is from package delivery. So it's a problem that PDDL and planners and the planning community are dealing with all the time. So the problems are standard.
Are there more questions? Wait, please. So the question will be recorded.
My sense is that in practice, a lot of these hybrid problems are solved using like domain-specific hacks that break up the problem and hence might be suboptimal. And those techniques often scale much larger than optimal solutions. Are you optimistic about the scalability of optimal hybrid planning kind of approach?
Okay, that's kind of high-level question. Yeah. Okay, so bottom line, yes. Okay, so this will not fit every type of hybrid planning problem out there. Okay, so it's only problems that you can approximate with, at least in my case, a second order dynamics. Okay, with quadratic drag, but still it's fairly simple dynamics. What they usually do in practice in companies, and when they need to do that, they use in even simpler planners. They get this sequence of actions, they get some kind of assignments, and they by hand, they try to stitch the actions together, try to change the values, and try to make it work. Okay? So at least in those cases when the dynamic is not too complicated, I believe it will give an automatic way to get a solution. Okay? So no, it don't fit everything, but a lot of the problems for navigation and stuff like that, I think it will do good.
Okay, we have time for one more question.
So if I understand correctly, what you do is you get a plan from a planner,
yeah.
Which tells you from which point to go to each point, and then you use this control approach to verify the plan and see if you can actually complete the tasks, right?
Yeah. Action by action, yeah.
Action by action. So basically you do not have a planner that plans using this dynamics, but you have a planner using some simpler dynamics, doing some sort of, and then you verify using this.
Yeah.
So have you tried using your dynamics in a planner, like doing this in a search?
Okay, so the question has arisen, and there is a good question why we do that, the good answer why we do that. If you put that in the search, the optimization problem that you get is non-convex, okay? And when you use a first-order dynamics, you get a convex solution, a convex optimization problem, which you have guarantees about the solution and is very fast. That's why we do want to rely on these planners. I call them simple model planners, but they are not simple. They're doing a terrific job, okay? But we want to use them. They are very fast and very reliable.
Okay, let's thank the speaker again.
Control P, I think, PowerPoint.
Ah, right, it's just F5.
Oh.
Okay.
Do you have your clicker here?
It's here.
Okay.
So the next talk, algorithm selection in optimization and application to Angry Birds, is presented by Shahaf, Shperberg, Avinoam, Yehezkel, and Solomon Ewald Shimony.
Okay, great. Thank you for introduction. So I'll start by presenting the game of Angry Birds. This is a popular video game, which is physical simulation based. In this game, you have different type of birds, and you have different type of obstacles and structures. Each bird has different ability, and you are given a set of levels. This is basically a puzzle game, and the goal of each level is to eliminate all of the pigs in the level. And you can do that by either hitting them directly with a bird, or make the structures collapse on them in a difficult and magnificent way. So our motivation for this paper was the AI Birds competition. This is an annual competition of autonomous agents that play the game. It takes place in Ijka every year. And the agents have black box access to the game, same as human players. And in order to evaluate their ability on the game, they are given 8 unseen levels that the competition maker presents to the agent for the first time, and the total budget of 30 minutes in order to solve the levels. So the utility that the agents get during the competition is the maximized sum of best scores of each level. So an agent can play a level as many times as he wants, but only the best score counts, and you sum up all of these scores for each level and get your total utility. And there are many good agents in the competition, and they all have different strengths and weaknesses. There is no one algorithm that dominates all of the problem instances presented. So this brings me to the next notion, the notion of algorithm selection, which was first presented by John Rice at 1975. Under this formulation, you get a problem instance up there and a set of algorithms which can solve the problem instance. And your goal is to choose the best algorithm to solve that specific problem instance. So in order to do that, you extract features from the problem instance. And using these features, you select an algorithm that will try to solve the problem instance. After selecting the algorithm, you apply it on the problem instance, and then you get a utility. So sometimes the utility can be the runtime of the algorithm, if it's a decision problem, let's say SAT. And sometimes you can apply a set of algorithms or a portfolio of algorithms on a single problem instance, but only if you can run them in parallel or interleaved. But this is not our case, because we have only one instance of the game, and we can run several algorithms in parallel or even in interleaved, because we have only a single set and we can interrupt a run of a single agent. So this notion of algorithm selection was actually applied to the game of Angry Birds by Stephenson and Rentz in 2017. It was called the hyperagent. They extract features on previously unseen levels. They used machine learning models in order to predict each agent's expected score on the level. They rank these agents based on the expected score. And they select the agents for a given level according to their ranking without repetitions until they played all of the agents or they managed to solve the level. And they're playing all the levels, all the 8 levels in a round-robin policy. So the method actually did quite good. It managed to improve all of the sub-agents it used, so it performed better than the agents that the hyper-agent used. But we still claim that there is some room for improvement. I'll try to convince you in the following slides. So the first issue that I have with this approach is the usage of expected score. And I'm going to try to persuade you why expected score is not always enough. So consider this toy example in which we have a single level, and we have k plus 1 agents and a time constraint of k. And each agent execution take a time of 1. So we can execute k agents on the problem before terminating and returning the utility, which is the best score achieved. So we have our first k agents on the left, which has a score of 1 with a probability of 1. Whenever they play the level, they get a score of 1. And we have our last agent on the right that fails 50% of the time, get a score of 0. And in the other 50%, it wins the level and gets a score of 1.95. So if you look at it in terms of expectation, the first k agents have an expectation of 1, and the last agent has an expected score of less than 1. So what the hyper agent will do, it will play agents 1 to k and get expected utility of the level of 1. But if you think about it, after you play the first agent and you get a score of 1, it's futile to play the rest of these agents, agent 2 to k, because you'll always get a score of 1. You cannot improve the score. And the rational thing to do is, after playing the first agent, you should play agent k plus 1 multiple times until you run out of time, in order to maximize the probability to get the 1.95 score. So if you use expected score, you cannot differentiate between the two situations, and you won't know what to do. The second problem is the usage of the round-robin policy. There are some level selection challenges. For example, there can be levels which are very hard to solve, and you can get very little score from them. There are levels that simply can consume too much time, and you won't be able to play them on time. And sometimes you want to reply promising levels even if you manage to solve them. So if I believe that I can solve the level better, for example, with less birds, and I can do it relatively quickly, I would prefer that than trying a level which I believe that I can solve efficiently. So what I'm trying to say here, that sometimes solving as many levels as possible is not necessarily the best idea, and not all levels were created equally. So we generalized the notion of algorithm selection to fit our settings. So instead of having a single problem instance, we have a set of problem instances. We still have our set of algorithms, but now we also have our time budget. So we start by extracting features on all of the problem instances. And now what we do is we're not only selecting algorithm, we select a pair of algorithm and a problem instance. And now we apply the algorithm on the problem instance. And after doing so, we get a score and time observations. So not only utility of the level, but also the time the agent took to solve the level. And if we have an additional time, we can repeat this process. Select a new agent and a new level, apply the new agent on the new level, and get new observations. We can also select the same agent and the same level, but this process repeats itself until we run out of time. So basically, our idea is to learn performance profiles for each agent and level, where a performance profile is a score distribution and a time distribution. And we use these performance profiles in order to select a pair of agents to maximize the utility under the time constraint. So we were facing with two main challenges. The first one is the optimizing the selections given the true distributions. And the second one is to actually learn the distributions. So we'll start with the first challenge. We introduced the max score problem, which is a 4-tuple IATP, where I is the set of problem instances we're trying to solve. A is the set of algorithms, T is the time budget, and P is the performance profile, which is a known distribution over instances and agents. And we denote by SAILII the observed score of a round, and TAILII the observed time of a round. And the process stops the first round, which passes the time budget. And the score of the process is, as I said earlier, the maximum value achieved for each level, for all of the levels in all of the rounds, when ignoring the last round which went over time. So the goal is to find a policy that maximizes the expected value of S, the expected utility. And if you look at our formulation, we can even use the max score problem when we have a single agent. And in this case, it won't be an algorithm selection. It would be a level selection. So we can use our methods in order to improve the level selection for a single agent and not only for algorithm selection, which is a nice feature. The problem is that the max score problem is NP-hard even in some very restrictive cases. The first restrictive case is when we have independent score distributions, deterministic runtime, and only a single problem instance. And the second one is when we have deterministic scores and runtimes and a single agent. So as you can see, these are very restrictive cases, but still they are NP-hard. We can, of course, try to solve the problem optimally by using a variant of the Bellman equation, which basically means compute the expected score below the time budget for every possible result of the executions of agents on levels. But this, of course, cannot be done practically. It's exponential in the performance profiles. And remember that we are at the meta level, so we need to make decisions really fast because we actually need to play the agents on the game. So we have our heuristic, which is called the improved rate greedy heuristic, which basically means that we need to choose a pair of agent and level that maximize the expected rate of improvement, where the expected rate of improvement is the expected score improvement. How much do we believe that the agent will improve the score of the level, times the probability we will actually finish on time, divided by the expected time it took him, given that he finished on time. So basically what we want to do is to maximize the slope. And we evaluated our method based on distributions collected from the game. So we have different settings of number of levels and time budget. So for example, in the left, in the right, there is two level instances and 200 seconds time budget. And on the far left, this is the actual competition settings, 8 level and 30 minutes. And the y-axis is the score optimality percentage. So 1 is the optimal solution. And close to that 1, you can see our improved rate greedy approximation, which does pretty good. It always performs better than 0.9 of the optimal solution. While if you want to look at the hyperagent algorithm, which is using round robin and greedy based on the expected score, its best performance was 0.6 of the optimal solution, and it sometimes performed as worse as 0.2 times the optimal solution. And even if you take the agent with the max performance for each of these settings, you do not get good results. So if we know the distributions, there is really potential for improvement when we use the max score settings. So now the second problem is to actually learn the distributions. So to learn the distributions, we first need to extract features and collect statistics. And then we need to learn the time and score performance profiles. So for the features and data extraction, we actually used the standard set of features for Angry Birds, which is the number of birds, number of pigs, and so on. And to collect statistics, we play our set of agents on the set of available levels multiple times and log the score and time results of the agents. So this was relatively easy. As for the performance profiles, we assumed that the performance profile of an agent on an unseen level is equal or almost equal to the performance profile that the agent has seen before on some level in our database. So what we do, we learn distribution over existing performance profiles using the features, and then we update these distributions based on our observations. So for example, a performance profile of agent A on level L can look like this, which is a distributions over performance profile. So for example, with a probability of 0.2, our performance profile could be a normal distribution because the agent has seen a normal distribution when he played an existing level. And as for our dependency model, we were using a naive-based dependency model, so we could update our belief according to the observations. So the FL is the features of the level, and down below the TALI-SI and the SALI are the observations of time and score when we play the agent on the level. So once we get an observation, we can do a Bayesian update in order to update our distribution of distributions. So now we have our learning scheme, and we wanted to evaluate it combined with our max score problem. So we're going back to the same setting earlier, and this time the one above is the optimal solution with known distributions, and below that is our meta agent, the Berg. And as you can see, it still performed quite well. Not as well as before with known distributions, but the learning scheme is reasonable, and we still managed to improve over the round greedy policy and over the single max agent. We're almost always dominating, except for that case over there. So now we wanted to actually evaluate our approach on the game itself, and not only on statistics collected from the game. So we played the 2014 to 2016 AI Birds competition levels. Each one had quarterfinals, semifinals, and finals. Each of them contained 8 levels. And we applied our algorithms and the existing algorithms on that set of levels. And as you can see, the sum of utility for each of these settings by our meta agent was the highest. And it actually won most of the rounds. And it even managed to outperform the hyper agent most of the times, even though the hyper agent has access to more agents, because Stephenson and Renz are actually the organizers of the competition, so they had all the agents which they could use, but we had only 4 agents listed below, which are the open source agents. So even though we had less agents, we could still perform well. So to conclude, we proposed an MDP model for optimal agent and level selection. This model is also applicable for optimal level selection given a single agent. This is hard to solve, but we have a good heuristics that works well, at least for the Angry Birds domain. And we suggested a naive Bayes learning scheme, which we can combine with our MDP model. And finally, we provided and evaluated a meta agent that actually plays the game and does that quite well. So I'm done, and if you have some questions, I'll be happy to answer them.
Questions? None so far. I was just wondering to which other domains your technique might generalize. Did you think of this?
So you need a domain in which you have a set of problem instances, and you have a time budget that can be applied to the entire set of problem instances, and you need to have different characteristics for each problem instance. Perhaps in the Angry Birds domain, each level had a different set of features, and you can achieve a different utility in each level. So there were some levels that had many objects, and you could reach scores of hundreds of thousands, and some levels were small, and you could reach very low scores. So you need to take that into the account as well. So any such domain, our method could apply to it. But you still need to invest time in collecting statistics on that domain and collecting the set of agents on that domain. And once you do that, you can use our methods as is. Yeah, and also situated temporal planning.
More questions? Okay, just a very open question. Do you see other room for improvement, another future work, how to get even better results?
Yeah, so I think if we can improve the learning scheme, because it was pretty naive. We used a naive Bayes model, and we collected statistics, and we had to compute distance between the set of features of an unseen level to the existing set of features in our database. And we can do that part better, because computing a matrix between a metric distance between an unseen level to all of the levels in the database is not an easy task, and we can improve that part.
There's time for one more question, maybe? If not, then let's thank the speaker again.
Thank you very much. The battery, because perhaps.
Low,
I think you should.
Subsession of this session. We'll have 3 presentations, all full papers, and the first one will be by Conny. It's joint work with Pascal Bercher on eliminating redundant actions in partially ordered plans, the complexity analysis.
Okay, thanks for the kind introduction. So, as the title already says, I would like to present our work, and our aim was to remove redundant actions in partially ordered plans. And I think it goes without saying that we are always interested in a cheapest solution, but finding an optimal solution might take much more time than just finding some solution. So an approach could be to just post-optimize a plan afterwards. Then in the context of mixed initiative planning, where a human is integrated into the planning process, so for example MapGen, the system that is used for the Mars rovers, there might be some change requests, so a user might ask to remove, or whether it is possible to remove an action, or there might be some parts of the plan that are planned completely by a human, and if the domain is very large and complex, it could be difficult to overview all possibilities and consequences, so maybe it could be good to post-optimize such a plan. Then, if we think of plan explanation, a human might ask or can ask of a justification of a specific action in a plan, and that explanation might be doubtful if the action is actually not needed. And last, assume you already found a plan for some planning problem, and now you need just a subset of the goal description. Then instead of planning from scratch, we can just try to find those actions that are actually needed. So before we go more into detail, I would like to introduce, quite informally, the partial order causal link planning. It is based on strips planning, I think you're all familiar with. So we have propositional state variables, an initial state, a goal description, actions with preconditions and effects. And what could be new to you, that those actions that can be just partially ordered, and there are so-called causal links, which make the implicit causal relationship between actions more explicit. So in this example, the precondition of the so-called consumer B is supported by the plan step A, and there might be a causal threat if there's a third action which can delete this precondition and can be ordered between those two. So in this case, C is neither ordered before A nor B. And then a partial plan is just a tuple which consists of so-called plan steps. They are actually just actions together with a label. And there's a partial order on these plan steps and a set of causal links. And then such a partial plan is a so-called partial order causal link solution plan, if and only if all preconditions are supported by causal links and there are no causal threats. So, and we describe the goal state and the initial state as artificial plan steps which are in the beginning and at the end of a plan. And if this criteria is satisfied, then all linearizations are solutions in the classical sense. So I would like to start with a small example. So we are given a Pockle plan, and we want to remove or try to remove the plan step P star. And what we can observe is that not every linearization afterwards is still executable. For example, if we order A1, A2, A3, and then B and C, then precondition of B is not satisfied anymore. But we could just turn C and B, because there's no ordering between those two, and then this linearization is a solution. So what we can see is that after deleting a plan step, there might be some linearizations which are not a solution anymore, but some may are. So this is the motivation for our problem. So we are given a Pockle plan for some planning problem and one plan step which we want to remove. Now the question is it possible to make this plan step, this plan without the plan step? Is there an ordering refinement of this plan? Without this plan step, this is still a solution. So we mean by this that we are allowed to add ordering constraints and causal links, but we are not allowed to delete any. So we want to repair this plan. And it turns out that remove and repair is NP complete, and membership is quite easy because we can test in polynomial time whether the Pockle solution criteria are met. And the hardness proof is based on a newly defined problem which we called cycle dissolving pairs, which is NP complete, and it somehow reflects the complexity of the first problem, but it's easier to handle. And we reduce CDP to remove and repair. So CDP is a problem from graph theory. So we are given a directed graph and a partition of the subset of its vertex set such that each element has size 2. So there are lots of pairs in this graph. And the question is it possible to make G acyclic by deleting at most one vertex of each partition element? To give you a small example, there's a directed graph, and one partition element is C and F, the other one is A and E. And now we can delete, for example, C and E, and the graph is acyclic. A slightly different example here, in order to dissolve the cycle at the bottom, we must remove A, but then we can't remove the cycle on the right because we are not allowed to remove E. Okay, hardness proof is based on a reduction from 3SAT. So we're given a SAT formula which consists of Boolean variables and clauses, and we construct an instance of CDP in the following way. For every Boolean variable, there are, maybe I can take, so there are 2 vertices. So for example, xj and not xj, and they form a partition element. And moreover, for every clause, there's a cycle consisting of 3 vertices, and every vertex in the cycle is linked via a partition element and a cycle to its corresponding Boolean variable. And to give you an idea of the mechanism, we, for example, remove xj, which corresponds in our SAT formula to setting xj to true. Then the cycle is dissolved, and then we can, for example, remove this vertex, so also this cycle is removed. But in order to dissolve this cycle, we must remove y, but then we are not allowed to remove c, and c23 belongs to the third variable in the second clause, which is not xj. Okay. So now we want to reduce this problem to our remove and repair. So we are given an instance of CDP, and we want to construct an instance of our remove and repair problem. So we need to construct a planning problem and a plan. So in this case, for every vertex, there's a literal in the goal state. And for every vertex vi, there's an action ai, which has li as a positive effect. And the edges correspond to negative effects. So for every outgoing edge, for example here from V1 to V2, there's a negative effect. So A1 has a negative effect, not L2. The same for the outgoing edge from V2 to V3, there's the negative effect, not L3. Then for every partition element, there are two actions. And so for example here we have V2 and Vn as one partition element, and there are two actions. So B has as precondition L2 as effect Ln, and C is just the other way around. And at last, there's the plan step P star, which just has all literals as add effects. And if you assume that there's an ordering from left to right, so the A's are ordered before P star, and so on, and there are causal links from P star to all preconditions here and here, then this is a Pockle solution. And in our instance of remove and repair, there's one plan step that we want to remove, and in this case, it is P star. So what we proved in our paper is that if there's a solution, so there's an ordering refinement of this plan, then we can turn this graph acyclic. And again, I just want to stretch the idea. So you might already saw that the effects here of the actions A form something like a cycle. So no matter how we order A1, A2, A3, there's always one literal not true at the end. But we can, for example, order C before B. Then L2 is satisfied in this case. So when we order C before B, it is reflected in the way that we removed V2 from the graph. So the ordering here says which vertices are removed, and then we can put all those removed vertices, the corresponding actions, just at the beginning, and put the other actions in the order which is given in the graph, so according to the edges. Okay, so I think maybe you got the idea, but you can read it in. Okay. And after proving the NP completeness, we were also interested in which structures in the plan makes the problem difficult, or which structure is corresponding to the exponent in the running time. And I claim that if we just pick or guess a linearization of, or an ordering of the actions B and C, then we can find in polynomial time an ordering of the A's. So in a more general graph, those B and C's we call attweens, and these are those plan steps satisfying the following three properties. So they are ordered behind the removed plan step, can be ordered before plan steps with unsupported preconditions, and can support any of these preconditions. So again, the example from the beginning, B and C are ordered after P star, and B can support precondition of C and the other way around. So B and C are the attweens. And the possible algorithm to solve this problem is just to try all linearizations of the attweens and find an ordering of the remaining one. But unfortunately, there can be exponential many of those linearizations, but at least we can say that remove and repair is fixed parameter tractable in this parameters and the amount and the number of attweens. And to sum up, I just want to point out some interesting differences between totally ordered plans and Pockle plans. And so if we consider totally ordered plans and we are given an action which we want to remove, we can just execute the remaining plan steps or the remaining actions and test whether this is still executable. So we can test it in polynomial time. And we could just do this for every action. So it is still in P to test or to test whether there exists an action in a totally ordered plan which can be removed. The same goes for K given actions. And Fink and Young and Nakost and Müller, they showed that it is NP to complete to decide whether there's a group or there are K actions which can be removed from a totally ordered plan. And as we saw in the last slides, in the case of Pockle plan, if we can repair such plans, it is already NP complete to decide whether one given action can be removed such that the remaining plan is repairable or not, and the remaining cases follow more or less directly. Yeah, that's it. Thank you.
So we're on time for some questions. Don't be shy, as always. Otherwise, I'll start. Okay, so one, like, you know, when we see there's something we'd like to do, I mean, you mentioned, for example, planning with humans in the loop, they want to remove an action. Now we have a difficult problem. We still need to do something about it, right? Like, where do we go with this complexity result? What can we do? Is it just like a too rich a notion of repair? Is it, or I don't know, is it fine even though it's NP complete? What would you say about how to address it?
I think, as we saw in the last slides, so that is fixed parameter tractable, that those, I think that the adjoins are not that much, so, or not that many, so I think it could be possible to still solve this problem quite, you see, yeah. But it's just a guess, so maybe we should pick some real-world domains and look at these plans and then count maybe the actions so that we can have a feeling of how large is this set.
You know, I could go on all day, but okay, Joerg also has a question.
I'm just a little confused about the contribution. Like, a cycle dissolving pairs is a known problem, right?
No, it's new. So
okay, so you invented this for the purpose of the proof.
So yeah, right. We invented it.
Okay, cool. And this was easier than just using set to reduce the original.
Yeah, somehow.
It was okay. You know.
I read the proof, and I must say it's a really, really nice paper, and that was one of the really nice parts, the coming up with a crisp, nice intermediate problem. So, you know, thumbs up for that.
Thank you.
And other questions or comments? I have one which is sort of related to my first one. So, I mean, the problem that you have here, that you basically have something which is essentially a solution, but you don't know that it's a solution, you don't know how to connect the causal links. I guess that doesn't just arise during repair, right? I mean, you might also, while you're actually searching for a partially ordered plan, sort of be in that situation. Is that like a practical problem for Pockle planning, or is it, I don't know, just the price we pay for the level of least commitment that we have in Pockle planning? Should we be worried about it? Like, you know, I have the plan right in front of me, but you know, I don't know it's a plan because I don't have all the ordering constraints.
Yeah, I think so. It's related to the result that if we just have the actions and we try to find those ordering, then it is NP complete, and I think it's somehow.
I guess there's always trade-offs. Okay, well, let's thank Conny again. And we move on to the second presentation. So the second presentation is by Alex Shleyfman, again, of course, given the name of the session on a complexity problem. It's on a complexity problem. I'll help you switch to the right screen.
Hey, oh, cool.
So it's related to symmetries. Oops. Ah, okay.
No,
You're testing the
checking
clicker.
the
Okay,
clicker.
okay.
Yep.
It's on the complexity of of checking for automorphism groups in classical planning. And Alex, you have the stage.
So my name is Alex, and welcome to the happiest session of ICAPS when people tell you about stuff you can't do. And I'm going to talk about computation of automorphism groups for classical planning. I kind of assume that everybody know here what FDR is, since, well, it's ICAPS and classical planning. Let's just repeat it. We have variables, each has a finite domain, set of actions, initial state, goal state, and you want to find a plan from the initial state to some goal state. Yay. So how would you do that? I assume that you should pick your favorite forward search algorithm. If you want to pick, say, another algorithm, I don't know why would you do that, so let's stick to forward search. Pick a heuristic and pick some secret ingredients to improve your search, because only heuristic probably won't help you to win the IPC, if you really want to win the IPC. And suppose that's the search tree that you have received after searching for a plan. It's nice, but suppose I tell you that the whole graph looks like this. It's kind of implying that if I remove, if I remove half of the states, I still find optimal solution. And that's what symmetries are about. You want to remove symmetric states to reduce the search space to find the solution more effectively. Okay, now the easiest way to think about symmetries as a relabeling. Basically, symmetry is a relabeling of your planning task. You change the names, but the planning task remains the same. And we want to know how hard to find those relabelings. So it was done numerous times. The works in black were concentrating on some subgroups. I'm going to talk about the works in magenta. They all compute the automorphism group of the compact representation. Obviously, you cannot compute the whole automorphism group of the transition graph, because usually the transition graph is too big and may include billiard of states which are not feasible. And we see why it's not feasible in a second. So our question is in bullet 2. How hard is to compute the group? But before to start talking how hard to compute this, let's talk about how we compute this group. What we produce is a problem description graph. It's a color graph when you have vertices for variables. We are in FDR. Vertices for values, and vertices for actions. So suppose I would like to move track from point A to point C. The precondition will be track in A, edge from A to C. The effect will be track in C, edge from move to C. Also, think about loading a package to a track. Preconditions, package in A, track in A, effect, track in D. Load, package in the track. This representation, if you compute all the relabelings on it, will be equivalent to this representation, which is the algebraic one. Do not look at it. It doesn't really matter. We're going to concentrate on graphs. because it's hard to draw algebraic forms. Then I'll explain everything on graphs. So the proofs in other papers suggest that the group of the PDG is equivalent of the relabeling group of the compact representation, and all of them can be embedded into the group of the state transition automorphisms. It's probably bigger, but that's the one we can compute efficiently. Now the only question is, what is efficiently? And since we are in the complexity section, you can guess that I won't give you a happy answer. So motivation. Anonymous reviewer said that it's interesting, and that's why we will solve it. So we need some complexity classes. First, graph isomorphism. Deciding whether one graph is relabeling of another graph. It's called graph isomorphism. It's not known to be polynomial. It's not known to be NP-hard. It's probably somewhere in between. We'll see a bit of results. Graph automorphism. Given two graphs, decide whether this is the same graph under relabeling. There is a map that maps vertices to vertices and preserves edges. This is polynomial to many-to-one polynomially reducible to graph isomorphism, which means definitely not simpler. Okay. About the graph isomorphism, we have those results from 85 and 83 by Babai, Laks, and Zemlyachenko. We'll see those families again and again. And in 2017, Laszlo Babai suggested that this problem probably could be solved in quasi-polynomial time, graph isomorphism. And some other really important mathematician claims that this C will be equal to 3, which is kind of nice. It's not polynomial, but it's close enough. So what we would like to show is that the groups of classical planning are not less richer than the groups of the general graphs. Which means our agenda for the next 7 minutes is as follows. You give me a graph with some automorphism group. I give you a planning task with the same automorphism group. If we done this, according to those two theorems, we are basically in the same complexity class. Moreover, for each automorphism group, there can be constructed a planning task with the same automorphism group, which kind of suggests if and only if. So let's start easy. We will start with unbounded variable domain, which means I may have as many facts as I want under one variable. So here is our graph. That's a graph. Important. I actually don't talk about graphs. I talk about permutation of those graphs. So as you can see, there is one relabeling of this graph that will preserve it the same. This relabeling will map x upon, yes, x upon y. It will, z and w will stay the same, but x will be mapped upon y, and that's the only automorphism of this graph. Now we'll construct a planning task with the same automorphism group. So first of all, I will produce my values. Then I will make edges that will resemble undirect edge. Those dashed arrows are basically actions with precondition. Say this edge is has a precondition vy and effect vx. I assume I do not need to convince you that the relabeling of this graph will induce the relabeling of this graph and the other way around, right? Nice. Now we have facts, we have actions. All we need is variable and goal. That's our goal. Goal can be mapped only upon goal because we want our automorphism to be goal preserving. Nope. That's our variable. And that's it. So you give me a graph. I give you a planning task with one variable and the same automorphism group. The only problem is that the domain of this variable won't be bounded, which is kind of frustrating a bit. Also, just an intuition to those who has it, this graph, if you look at those vertices as atoms, is basically a PDG graph of delete relaxed strips. So on the way, we have obtained a side result that says computing the automorphism group of strips is also hard. OK. Yay, that's our result. So next step would be to compute, to prove the same theorem, but for planning tasks with bounded variable domains. And to make it in the same time harder for us and easier, we'll take the smallest bound possible, which is 2. So we will want to construct a planning task with n variables, where each variable has 2 possible values. Yay. The only problem is that, no, give me a second. So I will need to produce some mapping from graphs to variables, since that's our main computational particles. The most natural, at least to me, thing that connects graphs to planning tasks are causal graphs. Unfortunately, causal graphs are not that easy to map onto planning tasks. So what is above is a PDG of a planning task. What is below is the causal graph of the same task. Do you see the problem here? The automorphism group of PDG is in red. That's the permutation. So it's a cycle of 3. The automorphism group of causal graph is a cycle of 2. Those are not equal, but it's even more frustrating because 2 is not divisible by 3, 3 is not divisible by 2, therefore those can be a subgroup of each other. So the main lemma in the paper that I'm not going to show here states pretty much in simple words as follows. If you forgo the automorphism on the variables, on the values of the PDG, the group of the PDG will be isomorphic to a subgroup of the causal graph. I will repeat it. If you forgo the automorphisms of variables, the automorphism group of PDG will be embedded into the automorphism group of causal graph. Thus, what we want to like to show now is, given a causal graph, produce a planning task with the same automorphism group. But, short lemma before that, if you recall, we talked about all results holding for undirected graphs. Causal graphs are directed graphs. So let's prove a simple lemma that shows that undirected graphs are reducible to directed graphs. That's done as follows. Once again, take the vertices, keep them the same, but add another vertices for each edge. Here, as you can see, edge will be mapped on the edge vertex will be mapped upon edge vertex, vertex will be mapped upon vertex vertex, because dig out here is 2, dig out here is 0. And automorphism preserves degrees. Once again, automorphism that maps x to y will induce automorphism that maps x to y and exz upon eyz. Once again, just switching the whole graph. So we enlarge the amount of vertices, but automorphism group stays the same. All is left to show is causal graph mapped upon some planning task with the same automorphism group. So for each variable, we produce a variable of the PDG with 2 values that are not symmetric. So you cannot, since t is a goal value, f is not a goal value, f cannot be mapped upon t and the other way around. We also add an edge just for problem to be reducible. And then we just add the edges from f to f. So the automorphism group of this causal graph will be the same as the automorphism group of this PDG. And basically, we are done. So what we have showed, automorphism group of FDR with unbounded domain, automorphism group of delete relaxed strips and the FDR of bounded domain are all reducible to computing the graph automorphism problem. The complexity of computing the automorphism problem of G is unfortunately unknown. What is known that the fast node algorithm canonical forms, those are used by most of the algorithms to compute the automorphism groups, are at the worst case like this. Surprisingly, those algorithms work quite well and can manage tens and even hundreds of thousands of vertices, which means they can be used in planning. Yay.
So we're perfectly on time. We have time for some questions. In the meantime, it's not happened yet. Maybe you can mic yourself up, Daniel. You have no... you're mic'd up. Excellent. OK. So let's go straight to questions. Yeah.
Thank you for your talk. So at the beginning, you mentioned that a lot of the motivation for finding these automorphisms is to get symmetry that you can then leverage to make planning more efficient. So can you elaborate a little more on, once you find a subgroup of the automorphisms, how do you use that to actually make planning easier? Is it just to decrease your state space, or is there something else?
I will definitely decrease the state space, and yay, all those guys. Basically, that's what they do.
Oh, okay.
So that's not the main idea of the paper that I present, but what you have here is exactly different ways of using those automorphism groups for reduction of the state space.
All right. Thank you.
More questions? So I'm getting a bit behind the times. Like with your last slide, you mentioned that we can more or less efficiently compute the canonical representatives. No one's doing that, right? People are using incomplete algorithms still, or?
No, they're using complete algorithms.
OK, I am behind the times. OK. I mean, by people, I mean us in planners.
Since we use SASI, Bliss, and all of them, they actually compute the whole group.
No, I meant the finding the canonical representative. I thought that was what the last slide was about. Maybe you can go there.
But that's
like the thing we do during such. I mean, I agree. We find the complete automorphism group.
Yeah, after
but
you have
to detect the duplicates, we still use something incomplete, right? Like we don't really find the canonical representative.
No. That's not the canonical representatives that we use. That's the canonical representatives that people from group automorphism use to produce those automorphisms.
Okay. Thanks for the clarification. Yeah. Okay. I see. Okay.
They call it canonical forms. But like people like the word canonical and.
Only because you're not a co-author this time.
Thank you. So, following on Malte's question, so what do we know about the complexity of finding canonical representatives of the...
Well, what do we know or what do I suspect? I suspect we don't
that's
really
the same.
I currently suspect that should be NP hard, because eventually it all is reducible to finding a path on the Cayley graph. So basically, the largest possible orbit that you have is a Cayley graph built from your generators. Unfortunately, you have a Cayley graph, and then your canonical labeling, like canonical order that you use, basically induces some order on this graph. And you would like to find a minimum on this graph, right? But since you don't really know in advance what are the structure of the graph is not connected to the weights of the vertices that you use. Thus, you will need to go over the whole graph. And in the worst case, the Cayley graph can be exponential in the size of the, since Cayley graph produces you the group. It has the same amount of vertices as the group has variables. Most of the time, in our case, in planning, what you have is our orbits are subgraphs of this Cayley graph. And we use incomplete techniques, and then why we do it efficiently. But for a general group, it probably will be NP hard.
We have to stop here. It was a long question. And actually, I have a follow-up question too. Let's do it afterwards. So thanks again.
Thank you.
And the third presentation will be by Daniel Gnad, joint work with Joerg Hoffmann. I think this is not a complexity paper as such. It's just a very complex topic. And it's about the relationship between star-topology decoupling and Petri net unfolding. So Daniel, please, we're eager to hear about that.
So thanks. And yeah, sorry about not having to show any new complexity results, just complex stuff. First of all, I want to thank Joerg, because I think without his help, I would not have been able to really formalize this stuff, at least in finite time. So thanks. A bit about motivation, because this is really somewhat a specialized topic. So why do we do this? First of all, you come up with a new idea, and the question is, has someone else invented this before or not, right? And as we will see later, decoupled search and Petri net unfolding are techniques that behave very similar in certain scenarios. So the question is really, do we do the same or not? The second, obviously, is like really gaining new insights by understanding why decoupled search works well, why in some cases it works less good than unfolding, and the other way around. We understand like about the techniques, so about the relation of the techniques, about the strengths and weaknesses, which is always good. It's like what research is about. So to briefly clarify the scenario, since Alex has already talked about classical planning, I won't go over it again. Just one thing, the goal here is not really relevant for us since we will always exhaust the entire state space. So we will always reason about the representation size of the entire state space. Our running example is, well, as usual, I have to say, sorry, some logistics task where we have one truck and we scale the number of packages. We have 2 locations. That's basically enough to show separations of the methods. As I said, we're talking about reachability checking, where given the conjunctive property G, we want to know if there exists a state S that's reachable from the initial state that satisfies this property. To do so, we built the entire state space. And now what's really the interesting fact is that both Star-Topology decoupling and Petri knot unfolding are methods that can significantly, actually exponentially, reduce the representation size of your state space, both by exploiting independence of components in your planning problem. Will be important later on is the notion of an exponential separation. So we would say that a method X is exponentially separated from another one Y if the representation of the state space of a task of X is exponentially smaller than the representation size of Y. Some known results, both methods are exponentially separated from explicit search, which is why well, people use those methods, because you can really, under certain conditions, you can very efficiently capture like the entire state space. Then the question is, how do the methods compare to each other? So let's briefly introduce both methods. For decoupled search, we are talking about dependencies of the state variables. Here our typical example is transportation, where we have a nice Star-Topology. We have the truck in the center. We have the packages all around, and the only dependencies here are from the truck to the center because the packages need the truck to be transported. We exploit this by only searching over center actions and at the same time enumerating all possible moves that the packages can do. So given a sequence of truck moves, the packages are conditionally independent, so we don't need to really multiply all options, but we just, for each of the packages individually, we enumerate all possibilities. Let's do an example. So in this box, you basically see the initial decoupled state of our running example. In the center, we have the truck. That's like a single center state. And all around for each of the packages, we have what we call the pricing function, which enumerates all options that the packages have. So each of the package can be at position L for a cost of 0. Well, obviously, because in the initial state, the packages are at L, so we don't have to do anything. But on top, they can also be in the truck if we choose to load the package in the truck, right? Package 2 doesn't care at all what we do with package 1 because they're independent. So those options are really like we can comply to any of those for any package, and they don't interfere. And now if we apply a center action, as I said, that's the only thing we do. We apply center actions, so actions that do something with the truck, we drive to the right. On top we get, so first of all the center state changes, and on top we get that now all packages can also be at position R. How do we do that? Well, we load them once the truck is still at L, then we drive and then we unload them together to a total cost of 2. Finally, we can drive back to the left position, which changes our center state, which does not change the possibilities for the leaf. And that's actually a complete representation of our state space. So even if we scale the number of packages arbitrarily, we still have only 3 decoupled states. Why is that? So basically, our initial state already represents 16 explicit states. So we don't need to enumerate all of them. We just compactly represent them in this structure here. And something that will be important later on is that you might now see that depending on in which order you execute center actions, this highly influences how many new states a single new decoupled state can represent, right? Depending on which preconditions a center action provides, you can basically reach more or less explicit states afterwards. No. Yeah, exactly. So, so say worst case, what we have, the guarantee that we have is that with every center transition we get at least one new explicit state. But then in this case, if with every center transition we gain one more explicit state, we don't have any saving in the representation size of our state space because we just do the standard search. And that's not what we want. Okay, so Petri nets, I guess you're not so familiar with this. That's why I want to spend some more time explaining this. In principle, when talking about planning, the places in a Petri net, which are the blue circles, directly correspond to our facts. So this blue circle down here basically encodes the truck is at L. And the actions are directly encoded by transitions, which are these gray boxes. In the Petri net, we connect places and transitions via the preconditions and effects of actions. So the drive right action has the precondition that the truck is at L. So there's an incoming edge here, and there's an outgoing edge to the truck at right, because this is like produced by this transition. A state in our planning task corresponds to a marking of the unfolding of the Petri net, and markings are represented by tokens in the places. So these black dots here are our tokens, and the state basically corresponds to a set of places that have a token. Unfortunately, Petri nets have some limitations. Namely, they are not able to support prevail conditions natively. So those are preconditions where we do not change the value of the variable, like the precondition of the load action. We need the truck at the same position, but we do not change anything with the truck. This leads to a blow up in the unfolding, as you will see later. Another thing is that they do not support effect only variables, but we can compile those very easily without any overhead. So let's do some example in this Petri net. Oh yeah, by the way, this only shows a single package. If we scale the number of packages, we basically have this right block here that will be copied for every new package. So let's do this. Assume we perform a load action, then this, as I said, this consumes the tokens in the input places, so the package at L and the truck at L. So we need to consume this token, although the truck doesn't change. And in turn, we need to put back a token to the same place. So this is the encoding of prevail conditions in the unfolding. Say we drive on from left to right. Well, nothing special about that. We consume the token down here, and we place it up here. And now, say we unloaded the package at the right. Then again, we consume the two tokens, and one for the package, one for the truck, and we place both back to the position. So how do we check reachability for a Petri net? We do this via unfolding. And that's what I'm going to explain here. So we have a second running example, which is basically 4 binary variables that can be set from 0 to 1 using this set Ci actions and the set L action. And we have actions that reset 2 variables, like one C variable and the L variable, from 1 to 0 at the same time. Now, what does the unfolding do? It starts in the initial marking, like when we create our state space, we start in the initial state. And for every transition that we apply, we add a copy of the output places of this transition. So we start with the initial marking, like all these places down here. And then say with an arbitrary order, we add new transitions to this. We do this, by adding these output places of the transitions. Now, the interesting part in Petri nets is that they directly exploit independence of transitions. So as you see, those 4 actions or transitions really don't interact with each other. There's no cross interaction, and that's why we can just have them individually in the unfolding. And then we can later on combine them with configurations, which are basically sets of actions in contrast to paths in planning. And so for all transitions that are independent of each other, we can combine them to arbitrary configurations. So in this case, basically, we could choose to just apply set C1. We could choose to apply any subset of those to reach the respective states. Now, say we decide to later on also apply this reset C3 action, then we will see that this only leads us to a state that we have already seen, right? Because if we apply all predecessors of this reset, basically set C3, set L, to then reset, we get to the same marking as the initial state. And this is basically duplicate checking of Petri nets. We mark the reset transition as a cutoff, and we stop. And now actually, again, like before, this is a complete representation of the state space of this task. So as you see, it's really, really compact because of the independence between the actions. Okay, so let's get to our results. Something that's really important is the search order, because as I tried to explain already before, it highly matters in which order you expand states, because the outcome state may represent different numbers of explicit states. So say for decoupled search, we take a bad decision, we go down here. Again, every of these boxes is a decoupled state, and say every state down here only represents a single explicit state. Then what we do is basically we build just a standard state space, and we don't gain anything. If, in turn, we choose to expand this one state that can represent all states of our state space, the final representation is way more compact, and we can, once we get here, we can prune all other successors because the entire state space is already represented. In unfolding, it's actually the same. So if, say, we choose this search order that I just indicated on the last slide, then this is our representation. If on top we have some set actions that set two things at the same time to true, and we choose to apply one of these actions first, then there's no more concurrency between these actions. They produce different output places for the same facts, like this C2 equals 1 is now produced twice to keep track of dependencies. And in fact, in this case, the unfolding also blows up. So that's why we need the search orders to be compatible whenever we compare the two methods. And we do that by requiring the unfolding to always execute transitions first that correspond to leaf actions, because decoupled search does this by definition, so we require the unfolding to do the same thing. On top, we need that the order on center transitions coincides as well, because if we don't have that, again, we can have exponential separations in both directions, and we are really not able to compare the methods. Yeah, that's what I just said. So we have this nice lattice of results. So basically, there are 3 dimensions which are relevant for the comparison. One is the existence, or we allow or forbid prevail conditions in our tasks. The second is to allow or forbid multivariable factors for decoupled search. And the third one is the compatibility or not of search orders. So let's go through this. As I said, for incompatible search orders, say this is the bad case for unfolding. Since decoupled search has to explore all leaf actions here before applying the first center action, and this might enable our critical action that leads to this state, we save exploring all this down here, just because, say, we decided for unfolding to not expand all leaf actions. Then if this critical action has a leaf precondition that we need to get to reach this, then the unfolding just doesn't see that, goes down here and expands everything. So we can also have the other way around, where, say, due to a reached leaf condition that enables this action here, which we get in decoupled search, but not in unfolding, because there we just apply the center action first. The unfolding actually gets a compact representation, and decoupled search doesn't, which leads to the advantage of unfolding. Okay, so what about prevail conditions? As I said, for our running example, this is the compact representation of the state space of decoupled search. Unfortunately, or I mean, well, say good for us, the Petri net unfolding explodes here. Why does it do that? Say we scale the number of packages to n. Now the issue is that when we build the unfolding, these load transitions are not concurrent because they consume the token from the same position, right? So since you can only consume this token once, and in the unfolding you don't place it back, but you create a new copy, then none of these transitions are concurrent, and they all produce these basically n copies of the truck position. And now in the second layer, the issue is that any new action that say loads another package or tries the truck can choose between n+1 copies of this truck at L place. And the more layers you have, you get the explosion. So why do we actually need these different copies? Well, because places at a certain layer might not be concurrent, which means that they're not reachable simultaneously. So for example, this truck L here and the package 3 in the truck are not reachable at the same time, because you would have to consume the truck L token twice, which you can't. So the final condition was multivariable factors, or let's rephrase it to independent components within a factor. So for decoupled search, we factor our problem in components, and if within a component we have concurrent actions, then decoupled search cannot do anything. For the Petri net unfolding, like the other example, as we know, this is a complete representation of our state space. Now decoupled search, if say we set all these C variables to be the center factor, just has this typical explosion, this diamond that you see that we typically resolve with partial order reduction. You have n independent variables. You can set all of them independently from 1 to 0, and you get this diamond-shaped search space, which is exponential in n. And the point is, since this will be our center state space, decoupled search can really not do anything. And so if the center state space is exponential in n, well, no matter what the leaves do, it will still be an exponential state space. So to conclude, let's take a look at our results again. What I've shown you is basically the exponential separations. So the second to last row here, that if we only allow for prevail conditions and forbid multivariable factors and only use compatible orders, then decoupled search can, first of all, be exponentially better than unfolding. And the result in blue, we could actually prove that it dominates unfolding, so it can never be larger than unfolding. For the second case, where we allow for incompatible orders, I've shown you results that basically everything can happen. There's really nothing we can say about the comparison of the methods. If we allow for multivariable factors that have like concurrency within the factor and forbid prevail conditions and only use compatible orders, in this case unfolding can be exponentially better. And again, we were able to prove that unfolding dominates decoupled search in this case, so it can never be worse. These dominance results nicely propagate downwards. So if we basically enable all restrictions, so no prevail conditions, no multivariable factors, and only compatible orders, then the two methods, in fact, do the same. And above these two colored lines, there's really no way to compare them. So to conclude, the most important insight that we got is really, yay, we did not reinvent the wheel. Further insights, well, with prevail conditions, really unfoldings do not work well with those. Independence within a factor cannot be captured by decoupled search directly, but we need some other methods to deal with this. With incompatible orders, there's no way to compare the two, and we have these two dominance results. For future work, can we somehow get the best of both worlds? Do we actually want that? So one thing that might be possible is to use the compact Petri net or unfolding representation within leaf factors, because yeah, I mean you can easily fiddle around with the representation within a leaf. Doing more than that seems really, really tough. That's it. Thank you.
Bit over time, but it's the end of the session, so I guess we can have a question or two anyway. Florian, please.
Thanks. So I assume there are some applications where Petri net unfolding is used. Are there applications where you now might instead use decoupled search instead Petri net unfolding?
Yeah, so there's one thing I didn't talk about at all, namely that given a complete unfolding or a decoupled state space, reachability checking is NP-complete for a conjunctive property in the unfolding, but it's polynomial, obviously, in the decoupled state space. So there's definitely a big advantage for decoupled search if it reduces the explicit state space. So one interesting thing maybe is that last year we were able to apply decoupled search in model checking, and that's really where Petri net unfolding is quite popular, right? So they have these models where you have like communication protocols with a lot of concurrency, and I assume that whenever you can use Petri net unfolding here, it's also an option to use decoupled search. But still, I mean, as I've shown, there's always still advantages that the unfolding has, and Patrick and others have also shown that in planning. So there's really planning domains where if you do unfolding, you solve a problem more efficiently than with other planning techniques.
One more question, Bernhard?
I was wondering, these are just two methods to shrink the state space. Are there more, or are people looking for more ways to shrink the state space?
Well, I mean, obviously there are a lot more techniques, symbolic representations, for example, like binary decision diagrams, but also pruning methods, like symmetry reduction, what Alex talked about, but also partial order reduction. And many of these methods have actually also been combined with each other. So we've also introduced both symmetry breaking and partial order reduction in decoupled search. So this can be combined, and sometimes you can really like benefit a lot. Also, sorry?
You have to compare them to your spell.
Yeah, sure. I mean, we've done that already. That was like the missing piece was unfolding versus decoupled search. And for the other methods, we get somewhat similar results. There are cases where one dominates the other and the other way around. There are other cases where they are doing similar. Yeah, so the comparison to unfolding was like the missing piece.
Okay, let's leave it at that. Let's thank Daniel again.